what has been written to a file. This is only post-mortem analysis. So if something bad happened, you cannot prevent it. You can only find out later on. And another idea that came out is called browser-enforced embedded policies. And here the policies are embedded in a web page as JavaScript. And they propose white and black listing. So they assume that the web page designer has perfect knowledge about all the allowed scripts for whitelisting. But this is usually not the case. If you, for example, want to load an advertisement, you will not be able to know the script that's executed by the ad. The alternative would be blacklisting, which is called DOM sandboxing in their approach. So they could mark a certain div tag in HTML as untrusted, and this would not allow to do any JavaScript in the subtree of the document tree. But then again, advertisements are usually installed with JavaScript. So not allowing any JavaScript does not solve advertisement either. So this works only for very restricted HTML and JavaScript applications. Gatekeeper is a new approach from Microsoft. They did mostly static analysis for two subsets of JavaScript. One is called JavaScript Safe, which is statically analyzable. For example, they have no dynamic code execution, no evaluation of strings. But to be able to analyze more realistic scripts, they had to allow some constructs that are dynamic and are essentials for the operating system widgets that they have been checking. And I just did that based on the usage. So the most common constructs were added, other constructs were not added. So they found that 22% of all the samples that they had were neither in JavaScript Safe nor in JavaScript GK, and they had to be rejected. So the other, about 80%, could be analyzed. That's at least something. But the code base they used, because of the widgets, are very small, so it was around like 200 lines of code. But for a smaller JavaScript applications, you can even do static analysis, even if the language is very, very dynamic. And another static analysis that has been proposed is called staged information flow for JavaScript. Here you already analyze the known code, because that's your own code that's known from the server, and it can be analyzed before being sent to the browser. But then you have to check a residual policy that comes from integrating foreign scripts in the browser of the client. Here they are assuming that if you create field names dynamically, which is possible in JavaScript, so you could have something like adding two strings and then use this as a field name, then they do not coincident with statically known field names. So it's kind of easy to circumvent such a technique if you know that a website is using this. And they do not also support full JavaScript. They have some constructs that they cannot handle. But again, parts of JavaScript can be statically analyzed. And the newest approach that I have found is called ConScript, and it will be presented at Security and Privacy this year. It's coming from Berkeley and Microsoft Research again, Meyerowitz and Lifshitz. And this is again integrated into the browser, into Internet Explorer 8. And you can express some fine-grained application-specific security policies, and these are enforced at runtime. So they show 17 examples of policies. They even propose that you can automatically generate policies, which sounds very nice. And they have an information flow control type system that ensures that your policies are sound. So how does this work? They have something that's called deep advice. So the idea is similar to what we had in a different paper that I have presented before. But instead of rewriting something in the browser, in JavaScript, they interpose their policies directly in the browser. So this guarantees complete interposition. So if you say this function should be monitored, then the browser guarantees that no one can access the function without actually having the policy being run before. Again, they propose mostly like white and blacklisting approaches for critical functions in JavaScript and also for script introduction. And this allows to formulate some more complex policies, like you cannot create a link after reading the cookie, because that link could include your credentials. Right? If you read the cookie, you know the credentials and you can send them out. So how do they secure that advice? They have found out that policies are very tricky to get right, even if it's only like a few lines of JavaScript. And so they split up the code into kernel code that's coming from the host and the user code that is untrusted. And to protect against advice tampering, they modify the interpreter to enable isolated reasoning. And I've got an example here. So the first line shows a whitelist. For example, everything that comes from Google is supposed to be trusted. And then the around keyword installs an advice. So it says, when calling window.postMessage, do the function that's behind here as a parameter. And so this does check if the target is in OK origin. And if it's not, then it will throw an error. Otherwise, it will go back and call the original function, which is the first parameter, with the message and the target it was intended to get. Is the syntax here clear? No questions? Okay. So what could happen in JavaScript here? Someone could redefine the toString method, for example. So what an attacker could do is, the first time toString is called, they could return google.com. So when it is checked, if something is in OK origin, then this will be OK. But when it is actually called in the last line of the policy, then they will return evil.com. So you can see this is kind of tricky, right? So only the first time when the policy is checked, you are returning the right thing, and when it's actually executed, it's returning something else. Another attack vector that could be done here is function prototype poisoning. So what you could say is that each time you do a call to a function, you should do window.postMessage to evil.com. And so now if you call postMessage, what would happen is it is checked. And because you entered google.com, this will be detected as OK. But when the last call in the last function, in the last line of the policy is done, this will call the function from the function prototype. And so it will not call the original function, but it will call window.postMessage for evil.com instead. So as I said, JavaScript is a very, very dynamic language. You can pretty much change everything here, right? And this is one of the examples. You can even change what will be called at runtime. Another option that attack vector could be, you could change the prototype of object, which is the top of the type hierarchy. So you could install the string evil.com and say that this would match to true. And so now if you call post message with evil.com, it will not be found in OK origin. But then the finding mechanism will go up and go to the object prototype, so which is kind of the superclass, and it will check over there. And there it finds that evil.com is matching to true. So OK origin of target will return true. So again, this is a very, very dynamic construct. And this is not what the people probably writing the security policy had in mind. Another thing that could be done is changing the way that a get function of a property would work. This is not possible in all browsers, but it is possible in the most widespread browsers. You can even change how something works when a property is read. So for example, if you want to read the property evil.com, then this could delete google.com from OK origin. So this is a combination with attack 3. You can even edit the whitelist. So again, a very, very dynamic language, and it allows a lot of attacks. So what would be a safe policy for ConScript? In their paper, they define some new constructs. And for example, the to primitive makes sure that you first convert the target to a primitive, for example, to a string. And so you would not allow the first attack vector because it is only calling toString once. And then it will check with a hasprop. This will check only in the original object and will not go up to the prototype. So you cannot do prototype poisoning here. And then they have something that's called ucall, which will only do a call to the original object and also not go up to the prototype. And this will prevent all these attacks that I have shown you before. But they had to change the language for that, right? And with these constructs, they are very static. They can do static typing, and they have an information flow control type system that shows if a policy is safe or not. And this policy is safe. So what would be the shortcomings of this new approach? Well, whitelisting and blacklisting are mainly best practices. So you can prevent some problematic constructs, but you can only prevent something based on previous attack vectors. It's not a semantic criterion, right? So it's like virus scanning. If you have not seen a virus before, you will not find it. So it more cures the symptoms than the disease. And one other issue they have is they do not yet have some option to instrument a function that's created by a library call without trusting the library. Because when you load the library,